Okay, so before I explain to you the formula for the orthogonal projection, it's useful to know a little bit about unit vectors and what's known as the polar decomposition of a vector. So let's discuss this for a second. Remember, for example, that if you have two vectors, if you have the xy plane, then you have these two unit vectors which are I and j, right? But then these vectors point along the x-axis, y-axis, and they have unit length. But like you should just think of the x-axis and y-axis as just two straight lines, right? There are other straight lines on the plane. So you could, for example, take this line, right? And this line will be specified by some vector v, right? In the same way in which x and y are lines which are specified by I and j. And so we would just like to rescale. Right, maybe this vector, the one that you chose, happens to have like length 3. It's more convenient to use your reference vector to have unit length. Right, so if this has length 3 and you divide by 3, you get length 1. Right, so that means that there's associated to this vector, there's a rescaled version of it, which I'm calling let's call this v hat, or e sub, let's call it e sub v. Okay, and so e sub v is a unit vector in the direction of v, right? And so this means that e sub v is simply, well, again, it's just a rescaled version of v, so you should just divide v by the norm of v. So this should be 1 over the norm of v times v. Okay? And so this is the unit vector. And so, for example, let's say that v happened to be 1, 3. So if v is 1, 3, the unit vector associated to v is 1, 3 divided by the norm of 1, 3, which is 1, 3. What's the norm of this? Well, this is the square root of 1 plus 9, right? Because it's 1 squared plus 3 squared. And so this gives you 1/3 over 10. Okay. Now another. Okay, so this is what unit vector means. It's the same definition if the vector is not on the xy plane, but rather on xyz space. Now, how's another way that you can think about this formula? If you look at this formula, you can just write v equals right, this is a number, so you can multiply both sides of the equation by norm of v. Okay? Right, so that tells you that any vector can be written as some number times a unit vector. What is a unit vector? Okay. if you think of a unit vector as a vector of size 1, that means that this is a point on the unit circle, right? Because this has size 1. That means that here you can draw the unit circle. Okay, and so this ends on the or specifies and this is like a norm. And so this is precisely the vector reinterpretation of the formula that z equals r times e to the I theta, if you remember complex numbers, right? So if you have complex numbers, you have this point z, which is x plus iy. And one way in which you could rewrite this is as, if this was an angle theta, as z equals r to the I theta. And if you run through the definition, r is like the size of the hypotenuse, so it's like what plays the role of norm of v, and e to the I theta is like the analog of this unit vector. Okay? So that's why this is sometimes known as a polar decomposition. And just for those who are curious, then you can apply the same logic to vectors in space. So there's a unit vector associated to this, which now belongs to the unit sphere in space. Okay? And so the point is that when you write, you can still write this formula where this refers to the radius of this vector, and this refers to a point on the sphere, which is no longer specified by a single angle, but as we'll see later, by two angles. The difference is that on the plane, you can think of this formula in terms of vectors or also in terms of complex numbers. But interestingly enough, like in 3 space, you cannot find like a version of this which uses like a 3D version of complex numbers, because there's no 3D version of those. But there's a 4D version of complex numbers, which are known as quaternions, which you'll know more about if you watch the video.